Last time we looked at the question of whether a given graph H appears within large Erdos-Renyi random graphs G and P in the limit as n goes to infinity and P scales in a given way with n. We stated a theorem which said that essentially there's a dichotomy. There's a range of parameter values for which, with high probability, there is no copy of H within this Erdos-Renyi random graph. And on the complementary set of the parameter space with high probability, there is at least one copy. And in fact, there are typically a very large number of copies. Okay, we didn't say what happens at the boundary between these two sets of parameters within the parameter space, but ignoring that, we fully characterized, the theorem fully characterizes what happens with regard to whether or not the random graph contains a copy of H. Okay, at least in the limit as n goes to infinity. And we proved one direction of this theorem last time. And this time we are going to prove the other direction. So if you have forgotten the theorem, take a moment now to remind yourselves of the statement of the theorem. We won't restate it again here, but we are going to turn directly to the proof. So I'll start sharing screen with you, and we'll work our way through the proof of the second half of the theorem. We are given a fixed graph H, and we introduce some notation. So we look at all possible copies of this graph, which might appear in the random graph G and P. So a potential copy that could appear is one which exists within the complete graph on n vertices. So HI is the ith such copy, and chi HI is the indicator that the ith copy of H appears as a subgraph within G and P. So it's contained within this random graph. Okay, so this is just a definition or notation for the indicator that the ith copy of H appears in G and P, where HI is the ith copy of H and Kn. So we look at all the possible copies of H that exist in Kn, number them in some arbitrary order, and chi HI is the indicator that the ith copy appears. Last time we computed the mean of, and NH is the sum over I of chi HI over all possible values of I. Last time we computed the expectation of this random variable by linearity of expectation. It's the sum of the expectations of the indicators. So we calculated the mean of NH and then used Markov's inequality to bound the probability that there is at least one copy of H in G and P. For the second half of the theorem, we are going to need the variance of NH, and we are going to use the second moment method, which involves using Chebyshev's inequality. Okay, so we begin by calculating the variance of NH in order to be able to apply Chebyshev's inequality. Now, the variance of a sum of random variables is the sum of the covariances. So this is this double sum over all possible values of I and J. The covariance of the indicators that the ith copy is present in GNP and the jth copy is also present in GNP. It's possible that the indices I and j take the same value, in which case this covariance is just the variance of the indicator of Hi if I equals j. Okay, so this is a general statement about sums of variances of sums of random variables, and we are using this fact, and it's a fact that you need to remember. Good. So now we turn to calculating the covariance. So what can we say about the covariance of these indicators, chi hi and chi hj? And this is going to depend on how much overlap there is between the copies hi and hj. And as we mentioned last time, though all our statements will be general, it's helpful to think of concrete examples. So the h we are going to work with is the square with one diagonal. So keep this example in mind. The statements I will make are general, but I'll also illustrate the ideas with this example in mind so that the arguments are easier to follow because we have a concrete example in mind. Okay, so let's calculate this covariance for different possible instantiations of these copies hi and hj. So what if hi appears on one set of vertices? So for a particular value of I and j, hi sits here, hj sits on some completely different set of vertices. Okay, what's the covariance in this case? So if this is hi and this is hj, and they have nothing in common, then the covariance of the indicators is 0, because by definition of the Erdos-Renyi random graph model, edges are independent, and we are asking about two completely disjoint sets of edges. So these indicators are independent random variables, and so we know that the covariance of independent random variables is 0. And if you don't know that, do remind yourselves of this fact. Okay. Okay, so these random variables are independent. Their covariance is 0 if they have no vertices in common. In fact, it's true as long as they have no edges in common. So if they have just, say, this vertex. Okay, so let me number the vertices. So maybe the first graph is sitting on vertices 1, 2, 3, 4. And the second graph is sitting on vertices 7, 2, 24. Now, in fact, the two vertices 2 and 4 are common to these graphs, but there are no edges common between these two graphs. And so the covariance is still 0 in that case, because the presence or absence of these subgraphs, hi and hj, is determined by these edges. And since we are talking about two disjoint sets of edges, they are independent. And so knowing that this particular subgraph arises tells you nothing about whether, so knowing this particular subgraph is present tells you nothing about whether this subgraph Hj is present or not, because you don't know anything about any of the edges of this subgraph. Okay, so that's one possibility. So here's another possibility. So maybe they have, maybe Hi is this. So we are repeating all the arguments we made for triangles. We studied triangles in detail, and I'm just repeating that, but in greater generality. So Hi is here, and Hj now is going to have this edge in common. So okay, so Hj is sitting here. And so they have this particular edge in common. So again, let me just number the vertices for convenience. Let's just call these 1, 2, 3, 4, 5, 6. So maybe Hi is sitting on vertices 1, 2, 5, 6 of the complete graph, and Hj is sitting on vertices 2, 3, 4, 5 of the complete graph with this particular pattern. And now the intersection of Hi and Hj, in this case, the bit that's common to both copies is this. So it's the edge 2, 3. By the way, let me also draw what's common to these two copies, Hi, Hj, we first looked at, whose covariance was 0. In this example, Hi intersection Hj, the intersection is not empty. It's the two vertices 2 and 4, but with no edges between them. Okay, the intersection of Hi and Hj in this example is the two vertices 2 and 4, but with no edge. So it's a graph that has vertices but no edges. Here we have two vertices and one edge. And there are other possible ways they might intersect. We won't go through all of them, but let me draw one more picture. So maybe Hi is this thing here. And now maybe Hi and Hj have this triangle in common, and Hj is this. So again, let me number the vertices. Okay. Hj consists of these other edges, so it's connected to so this particular vertex is going to be replaced by this other vertex. So we have the vertices 1, 2, 3, 4, 5, let's say. So Hi consists of vertices 1, 2, 4, and 5 with the diagonal. Hj consists of the vertices 1, 3, 4, and 5 with the diagonal. And so okay, so what is common is this bit. I'll draw double lines to indicate what's common. The triangle sitting on the vertices 1, 4, and 5 is common. Okay, so we've drawn some pictures to illustrate for general graphs. For a general graph H, if you look at two copies Hi and Hj, then they intersect in some way. Maybe the intersection is empty, but maybe it's not empty. Maybe it consists only of vertices. Maybe it consists of vertices and edges. The intersection doesn't have to be a connected graph. It might consist of pieces, disconnected pieces. It could be quite complicated, but there's some intersection. But no matter what the intersection is, it is necessarily a subgraph of H, right? Because it has to be part of Hi and it has to be part of, okay, it has to be part of Hi. So it has to be part of H. So it's a subgraph of H. It's a subset of the vertices, a subset of the edges. So something consisting of two vertices with no edges is a subset of H. Something consisting of one line is one edge is a subset of H. A triangle is a subset of H. In all these examples, we see that it's a subset. And the value of the covariance will depend on what exactly the subset is. If the intersection contains no edges, the covariance will be 0. If it contains edges, it will not be 0, but what it is will depend on what the intersection is. Okay. So let's work out what happens in general. But this, hopefully these pictures give you an idea of what are all the possible things that can happen in general. Okay, so let's calculate the covariance. So let's denote by H prime the intersection of Hi and Hj for two particular copies Hi and Hj of H. Then the covariance of these indicators by definition of the covariance, this is the expectation of the product the covariance of two random variables is the expectation of the product minus the product of the expectations okay, so the covariance. Okay, so this is the covariance. So let's evaluate each of the terms. Let's start with the individual expectations. This is easy. So what's the expectation of the indicator of Hi? The indicator is a 0, 1 valued random variable. So the expectation is the probability that it takes the value 1. So it's the probability chi Hi equals 1. So this is the probability that Hi is present in G and P. Hi contains EH edges. That was the notation for the number of edges in H. Each edge is present with probability P independent of the others. So the probability that EH edges are present is P to the EH. Okay, so we need this many edges to be present. More could be, we don't care, but we need at least this many edges to be present, specific edges to be present. And so the probability is P to the EH. And similarly, it's the same for the expectation of chi Hj. These are the same. Okay, but what about the product now? So what's the probability? Okay, again, what's the expectation of the product of these indicators? Each indicator can only take values 0 or 1. So the product again can only take values 0 or 1. And so the expectation of the product is the probability that the product takes the value 1. So it's the probability that the product takes the value 1, but that can only happen if each of the indicators takes the value 1. Okay, so we want to calculate what the probability is that both the copies hi and hj are present in the random graph GMP. So this is the probability that hi and hj are both present in GMP. In the random graph GMP. So now we are going to calculate this probability. And again, if you like, you can think of an example from one of the ones we drew earlier. So let's work that out. As before, to calculate the probability that something is present, we simply count how many edges there are in that for that event to occur. So the probability that hi and hj present in GMP So how many edges do we need for hi and hj to both be present? So it's p raised to the power the number of edges we need. So we need edges for hi to be present. We need another edges for hj to be present. But some of these edges are common. So if we had this particular pattern, so here h prime, so this is hi, this is hj, and they intersect in the subgraph h prime, which is two vertices joined by an edge. So this is just a single edge. Okay, so we need h edges for the first graph, h for the second, but we take away what's common. And what's common is the number of edges in h prime. Okay, so minus h prime. And let's just check this for our example. So h had 5 edges, so we needed 5 edges for hi, 5 for hj, and h prime had 1 edge in common, so in total we need 9 edges. And if you look through this figure, hopefully you can convince yourselves, okay, 1, 2, 3, 4, 5, 6, 7, 8, and the middle 9. So this has 9 edges, 5 plus 5 minus 1. Okay. So this is p to the 2 minus prime. So this is the probability that the two copies hi and hj, the two particular copies hi and hj are both present, and that depends on how big their intersection is. If the intersection was not an edge but was a triangle, then here we would be subtracting 3 rather than 1. So this is the probability that both are present, and so it's also the expectation of the product of these indicators. Okay, so we worked out that expectation. So the covariance of HI and of the indicators of HI and HJ is the expectation of the product minus the product of the expectations So the first one is P to the 2EH minus EH prime. Okay, minus the second term, we already calculated the expectation of the indicator of HI is P to the EH, and it's exactly the same for HJ. And that gives us P to the 2EH. So this becomes P to the 2EH minus EH prime times 1 minus P to the EH prime. Okay. And then we are looking at an asymptotic regime in which P scales like n to the minus alpha, for alpha strictly positive. So P equals n to the minus alpha, alpha bigger than 0. So n is going to infinity and P is going to 0 in some related way. So the graphs are getting bigger, but each edge is becoming more and more unlikely. So P is going to 0, so P to the EH prime is also going to 0, as long as EH prime is at least 1. The cases where EH prime is 0, we already know the covariance, that's 0. They are independent. So in all the cases that are of interest to us, EH prime is positive. So P to the EH prime is going to 0. So this is approximately P to the 2EH minus EH prime. Okay, so we are only interested in intersections which have at least one edge. Otherwise, the covariance is 0. Good. So we have calculated this J should be, sorry, there's a typo here. This indicator of J should be indicator of HJ. Good, so we have calculated the covariance for all possible intersections of indicators. So now we go back to the formula for the variance. So let's write the variance of NH is the sum over all I and j of the covariance of the indicator of HI and the indicator of HJ. And we saw that the value of this covariance depends on what the intersection of these two graphs, HI and HJ, is. The more edges these have in common, the bigger the covariance, and if they have no edges in common, it's 0. So what we are going to do, we have to do this sum over all possible copies HI and HJ, but we are going to group together terms in the sum. We are going to group together all those terms where the intersection is the same subgraph. So we'll group together two copies which intersect in just a line. We'll group together two copies which just intersect in a triangle. And similarly, we'll group together two copies which intersect in all other possible subgraphs. So I just rewrite the sum by grouping together terms of interest. So I look at, so this is the sum over all subgraphs H prime of H, including the whole graph. Now we look at those terms in the sum. We are grouping together those terms in the sum over I and j for which the intersection of hi and hj happens to be this particular subgraph H prime. And then the covariance of the indicator of hi, the indicator of hj. Okay, and without loss of generality, since this sum, this covariance is 0 if H prime contains no edges, so we can restrict the sum to H prime containing at least one edge, H prime bigger or equal to 1. Good, so let me just rewrite the sum. So this is the sum, H prime subset of H, consisting of at least one edge. And now, what's the covariance here when the intersection is H prime? We calculated that. It was some constant p to the 2 EH minus EH prime. Okay. It didn't depend on the particular values of I and j. So if you had the same pattern sitting at this set of vertices and overlapping in a certain way, the covariance was the same as if you moved it to another place in the graph. If it's the same pattern moved to another place in the graph, it has the same covariance. Why is that? That's because the edge probabilities are p anywhere in the graph. The edges are independent, but they have the exact same probability p anywhere in the graph. So whether a pattern is sitting on this set of vertices or on this set of vertices, it has the same probability. And hence the covariance doesn't depend on that. Okay, so we are summing over I and j, something that doesn't depend on I and j, but only depends on the intersection. So we have here p to the 2 EH minus EH prime times the number of terms in the sum. The number of terms, this constant is added up. And the number of terms in the sum is the number of copies hi and hj whose intersection is H prime. Okay, let me write that in notation to keep it simpler, such that number of copies hi and hj such that the intersection is equal to H prime. Okay, so that's what we have to count next. And we'll do the count, and then we'll do the sum over subgraphs. Okay. Good. So now we are going to see what this value is. How do we calculate this number of copies? Again, we'll only count this number of copies very approximately, ignoring constants and only focusing on how it scales with n, the number of vertices in the graph. Okay, maybe it's helpful to start with an example. So let's take this particular example. So we want to count how many times this particular pattern appears in the random graph. of two copies hi and hj intersecting in this edge. Okay, so in order to do that, we have, okay, so how many ways can this pattern appear in the complete graph? So we have to pick six vertices, and we can do this in n choose 6 ways. And why 6 vertices? Yeah, that's the more interesting question. So we have to pick, so we need, for this particular pattern, we need 6 vertices. And 6 is 4 plus 4 minus 2. 6 is lots of other things, so why have I written it as 4 plus 4 minus 2? So here is hi, here is hj. So we need 4 vertices each for hi and hj. Right, each of them has 4 vertices and 5 edges. hi is just a square with one of its diagonals present, so it has 4 vertices. And so we need 4 vertices for hi, 4 for hj, but 2 are common in h prime. H prime here was this. So H prime, these two intersect in one edge, 2 vertices and 1 edge. So 2 vertices are common, belong to the intersection, and so they are common in both. So we are double counting if we count them in each. So we need to subtract this. And 1 edge was common, but we are not concerned about edges at the moment. We are only concerned about vertices. Okay, so therefore we need 2 VH minus VH prime vertices, right, to see this pattern. Okay, so, and that happens to be 6 for this example. So we need this many vertices, and the number of ways of choosing this many vertices is n choose this, so n choose 6 in this example. Now, once we have chosen those 6 vertices, in how many ways can we put this pattern upon them? That depends on 6 factorial divided by the automorphism group of this, the size of the automorphism group of this particular pattern. But we don't care about that. Those are all constants. We don't care about that. Okay, so with that example in mind, in the more general case, so for one copy of hi and hj such that the intersection is h prime, we need 2 VH vertices. So we need VH vertices for HI, VH for HJ, but VH prime, the number of vertices of H prime are common to both, so we subtract that. So we need this many vertices in total to have this pattern hi and hj intersecting in h prime. Okay, and so the number of such copies is number of copies of these two graphs, hi and hj, intersecting in h prime in the complete graph Kn is n choose 2vh minus vh prime okay, times something. We don't care too much, but let me write it out. 2vh minus vh prime factorial divided by the size of the automorphism group of of this particular figure you get by getting two copies which intersect in H prime. But since we are only concerned in how this grows with n, this grows like n to the 2vh minus vh prime. And everything else is a constant that depends on the graph H. It depends on the graph H prime, but it does not depend on n, and it does not depend on p. Okay, so this is the number of such copies. That's what we need to keep track of. I don't know if that has gone outside the screen for some of you, so I'll write it down once more. So this was n to the approximately n to the 2vh minus vh prime. Two times the number of vertices in H minus the number of vertices in the intersection H prime. Good. So there are this many copies, and for each such copy, we know what the covariance is. So let's put all that together to calculate the variance. So we saw that the variance of NH was the sum over HI and HJ intersecting, okay, sorry, no, the sum over H prime, the sum over all possible subgraphs, the sum over HI and HJ intersecting in H prime of the covariance of HI and HJ, chi HI and chi HJ. And this we rewrote as the sum over H prime, subgraphs H prime of H. The covariance was approximately p to the 2eh minus eh prime times the number of such copies there can be intersecting in H prime, and now we calculated the number of such copies to be n to the 2vh minus vh prime. Okay, this is approximately this. And the sum is over subgraphs which contain at least one edge. And now I'm just going to substitute the fact that p is n to the minus alpha. And so this is approximately the sum over H prime subset of H containing at least one edge. of n to the p is n to the minus alpha. So let me group together terms in a certain way. It's n to the 2vh, 2 times vh minus alpha eh minus vh prime minus alpha eh prime. Okay, it's slightly messy, but not too bad. I'm not going to simplify this further. I'll just keep these terms with. So this is the variance. Note it down. We'll need to use it later. So this is the variance of the number of, this should not be h prime. This is all for h, sorry. This is the variance of the number of copies of h. Not sure why. Okay, let me. Fine, we've done the calculation. I'm not able to erase the right bit. So this is the variance of the number of copies of H in the random graph GNP. We have obtained this expression for it, and we'll use it now to prove the second half of the theorem. And for that, we are going to use Chebyshev's inequality. Okay, let me briefly stop sharing and restart sharing. Okay, so the question we are interested in is whether the random graph GNP contains at least one copy of H. So we are interested in this probability. And we want to show that in a given parameter range, this probability is close to 1. But this is just 1 minus the probability that the number of copies is 0. And so what we are going to do is try and show that the probability that there are no copies of H in the random graph GNP is tending to 0. So we want an upper bound on this probability. Now the probability that a random variable takes the value 0 is at most the probability that it deviates from its mean by at least its mean. I'll finish writing this down and then I'll talk. Okay, why is this inequality true? It's true because the event for which we are calculating the probability on the left-hand side is a subset of the event for which we are calculating the probability on the right-hand side. Why is meaning that if this happens, it implies that this also happens. Why is that? So what's the event on the right-hand side? If the random variable deviates from its mean in absolute value by at least its mean, that's saying random variable should either take values smaller than the mean minus the mean, which is 0. It should either take values less than or equal to 0 or bigger or equal to 2 times the mean. That's the event on the right. The event that it takes the value 0 is a subset of the event that it takes values less than or equal to 0 or bigger or equal to 2nh. That's all. So the probability here is bounded by that. But for the right-hand side, we have a good bound. So what's the probability a random variable deviates from its mean by more than some given constant that's less than or equal to the variance of the random variable? The random variable here is nh, divided by the square of this constant here, by the square of nh, enh. Okay. And this is just Chebyshev's inequality. Okay, and we have approximately calculated the variance and the mean here. So let's substitute that. So this is approximately the variance we saw was n to the 2 times V8. Sorry, it's okay. I'll need another page. Let me just go to another page and do the calculation. Okay, so we have the probability that there are no copies of H in G and P is bounded above by the variance of NH divided by the squared mean of NH and we've calculated the mean and the variance approximately, so let's use that. The variance was the sum over H prime subset of H consisting of at least one edge of n to the 2 times VH minus alpha EH minus VH prime minus alpha EH prime. Okay, so it was the sum, and now this whole thing is divided by the mean squared. The mean we calculated earlier was n to the VH minus alpha EH. Okay, so it's the square of that. The square of this is just n to the 2 VH minus 2 alpha EH. That cancels out the first term here. And what we are left with is the sum over all subsets H prime of H, subgraphs H prime of H consisting of at least one edge, containing at least one edge, of n to the minus VH prime minus alpha EH prime. Okay, so that's our expression for this ratio, the variance over the mean square. So that's our upper bound for the probability that NH is 0. Okay, so let me rewrite that on the next page as we continue our calculations. So the probability that NH is 0 is bounded above by a sum over H prime subgraph of H with various properties. Let me not rewrite that. Sum over H prime dot 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 of n to the minus VH prime minus alpha EH prime. Okay, what do we know about alpha? We are in the second half of the theorem, and for the second half of the theorem, the condition on alpha was that alpha is smaller than VH over EH. Okay, where these correspond to the original graph H, for which we are counting the number of copies in the random graph. So this was the assumption in the second half of the theorem, that alpha is smaller than this. But we also know that EH prime over VH prime is less than or equal to EH over VH. Why do we know this? We know this because we assumed in the statement of the theorem that H is balanced. It's a balanced graph. And this is the definition of balanced. Okay. If H is balanced, every subgraph has edge density no bigger than that of H. So EH prime over VH prime is less than or equal to this, or VH prime over EH prime is bigger or equal to this ratio here. Okay, so another way to say that is that alpha is therefore also smaller than VH prime over EH prime, because this ratio is at least as big as the ratio VH over EH, which dominates alpha. So let's put that all together on the next page. The probability that the number of copies of H in the random graph G and P is 0, that there are no copies, is bounded above by sum over H prime subgraph of H with certain properties, n to the minus VH prime minus alpha EH prime. But alpha is smaller than VH prime over EH prime, which means that this quantity here, VH prime minus alpha EH prime, is strictly negative. And that's because EH prime is at least 1. They are not both 0. We are only looking at subgraphs containing at least one edge. Okay, so we have something strictly negative in the exponent. So n to the minus this thing is going to 0. Okay, so for each fixed subgraph H prime of H, this thing here is going to 0 as n goes to infinity, this term here. We have a sum. The number of terms in the sum could be large, but there may be lots of possible subgraphs of H, but it's some fixed constant. It doesn't grow with n, right? It could be 100, it could be 10,000, but it's some fixed number which is not growing with n. And this thing here is tending to 0 as n tends to infinity. So even after summing, the whole thing tends to 0. Okay, so therefore, the probability that the random graph GNP contains no copies of H tends to 0 as n goes to infinity, which means the probability that it contains at least one copy of H tends to 1 in this range of parameters. Okay, and that completes the proof of the second half of the theorem. So we've finished proving the main theorem of this part of the course. So this part focused on local properties of Erdos-Renyi random graphs, meaning properties that are determined by some fixed number of vertices, a constant number of vertices not growing with n. And so we've finished looking at, we've proved our main result about the presence of any fixed small graph within the Erdos-Renyi random graph. In the next lecture, we'll turn our attention to global properties. We'll start by looking at the size of the largest connected component of a random graph. But I'll stop here with our discussion of local properties, and I'll stop recording.